Hello everybody, good morning. In this video today, I will go over the process of backpropagation in a neural network architecture and how the chain rule of differential calculus comes into play to calculate the weights and fine-tune the weights. So before going into the details of the process, let's quickly go over the overall what neural network is all about. So you can already see in this photo, it's a supremely basic and supremely simplified structure of a neural network architecture. So each neuron is connected to other neurons, but not all connections are equal. And that's where the concept of weight comes into the scene. And speaking more formally, in a neural network, a firing neuron propagates an impulse of 1 to the outgoing neurons, while a non-firing neuron propagates an impulse of 0. That's how you can think of it. So you can think of the weight as indicating how much of the impulse of the firing input neuron is forwarded to the next neuron via the connection. Mathematically, you multiply the impulse by the weights of the connection to calculate the input for the next neuron, like we are doing here. I will go over this calculation in a little bit more detail in a while. So the overall structure that we have here for this example, it's a very simplified one. It contains one hidden layer, which is this, with 3 nodes in it, and one input layer and one output layer. So every arrow in this diagram contains exactly one float value as a single weight that is adjustable, and that's what we will do. That is, we will adjust the weights to figure out the least possible loss to the overall structure. So totally there are 9 weights, 6 in the first layer, 1 2 3 here, 1 2 3 here, and 3 in the second layer. So totally 9, and we have input as 1 1, and the output should be, that is, we have to target the output to make it as close to 0 as possible. That's the problem here. And so when we fine tune these weights, that's what training is all about. And we have not introduced a bias value yet here for simplicity purpose only. The underlying logic remains the same, however. So in this step, we perform the multiplication of the input with weights to calculate the value of hidden units in the hidden layer. So for example, this h11 value, which is here on the first node of the hidden layer, that is derived by multiplying wx1 with w11, x2 with w21 accordingly. And we have given some imaginary number here as weight 0.8, 0.4, 0.3. So the h11 value comes out to be 1, h12 value comes out to be 1.3, and h13 is 0.8. And the by the normal terminology, how these subscript is determined, let's see the rule here. So when I said W12 or W22 or W11, the way that it is determined is that the first number in any weight subscript matches an index of the neuron in the next layer, and the second number matches the index of the neuron in the previous layer. So the weight here it's W11 because the next layer, the first node it's going to is 1, and the previous node is also 1. But this structure here, the second weight, that is here, W will be 1 2 because it's going to the number 2 node in its target, and it is originating that its previous node is number 1. And now the basic question, what is a neuron? A neuron is a container that contains a mathematical function which is known as an activation function, which takes inputs as x1, x2, which is the input values, and it also take a vector of weights w1, w2 in this case, and a bias term. A neuron first computes the weighted sum of the inputs like we see here, and passes it through the activation function. And what is an activation function? Activation function is simply a mathematical function that takes in an input and produces an output. Think of the activation function as a mathematical operation that normalizes the input and produces an output. The output is then passed forward into the neurons on the subsequent layers. And that's how the feed-forward motion goes on. So a feed-forward propagation's high-level steps can be summarized as below that. Number one, perform a sum product at each neuron, then compute activation function, repeat the first two steps at each neuron until the output layer, and then finally compute the loss by comparing the prediction with the actual output. And that's where one cycle of feed-forward propagation is done. And then the back propagation will start. So what we do in feed-forward propagation, we connected the input layer to the hidden layer, which then was connected to the output layer. In the first iteration, we initialized weights randomly and then calculated the loss resulting from those weights values. In back propagation, however, we take the reverse approach. We start with the loss value obtained in feed-forward propagation and update the weights of the network in such a way that the loss value is minimized as much as possible. So here are the high-level steps of back propagation. That is, start at the output layer, change each weight within the neural network by a small amount, one at a time, measure the change in loss, that is delta L, when the weight value is changed, that is delta W, and update the weights by minus k multiplied by del L del W, where k is a positive value and is a hyperparameter known as learning rate, and del L del W is a well-known thing called the gradient of loss with respect to the weights. So why computing this gradient that we just discussed in the previous steps here, that is update the weight by learning rate multiplied by the gradient. And to answer these, we first need to revisit what some of the basics of calculus, differential calculus to be specific. So gradient of a function c, in this case c is a function of x1, x2 and so on. In point x is a vector of the partial derivative of c, and that is given by like this, that is del c del x equal, that is, which is a vector of del c del x1, del c del x2 and so on. The derivative of a function c measures the sensitivity to change of the function value, that is the output value, with respect to a change in its argument x, which is input value. In other words, the derivative tells us the direction c is going, and the gradient shows how much the parameter x needs to change in positive or negative direction to minimize c. And in this case, we want to find the change of the loss with respect to the individual weights, and we'll come to that in a while. Let's move over. So how does a neural network update weights and biases during a backpropagation? And the answer is backpropagation reduces the error by changing the values of weights and biases. To do this during the backpropagation, we calculate the rate of change of error with respect to rate of change in weight. That is this term, the gradient del L del W. And note that the update made to a particular weight is proportional to the amount of loss that is reduced by changing it by a small amount. Intuitively, that makes sense, because if changing a weight reduces a loss by a large value, then we can update the weight by a large amount. However, if the loss function is small by changing the weight, then we update it only by a small amount. And those calculations, those rate of changes are all determined and controlled by this all-important factor gradient, that is del L del W, and we will calculate it with the application of chain rule of differential calculus. So now, before going into the details of actual calculation of the chain rule with differential calculus, let's understand why we need the chain rule in backpropagation at all. So far, we have calculated the gradients of loss concerning or with respect to weight by updating the weight by a small amount, and then calculated the difference between the feed-forward loss in the original scenario when the weight was unchanged and the feed-forward loss after updating the weight. That was our original proposition during the backpropagation. But one drawback of updating weight values in this manner is that when the network is large, containing thousands and millions of nodes and weights, which is very normal in with real-world dataset, a large number of computations are needed, and so that becomes almost impractical in few cases. And how that happens, let's check out the actual mathematics of that. So we already understood that our loss or the cost, which is at the output layer, it's C, and it's a function of weights, that is W1, W2, W3, and so on. So you number the weights with W1, W2, and want to compute the gradient, that is a change of the cost or the loss with respect to the weights and each of the weights. So what we want to compute is del C by del Wi. It's C actually. Sorry for the bad handwriting. And the Wi represent each of the weights. It could be in millions with real-world data set. So an obvious way to do this is like below. Let's go to another slide. Del C by del Wi equal to, it will be we already know that C is a function of weight, so we are changing the weights like so. We have to update the weight by adding a small amount of weight, and then compare the difference of the cost function with the original weight. So this is what we do. We update the weight here, that is W plus adding a small amount. Let's denote it with not like this. Let's use epsilon and EI. I will explain what these terms are in a while, and deduct the original function, divide the whole thing with a small amount. So here this symbol epsilon, it's actually here it's a small amount and greater than 0, and EI above, that is this term here, is the unit vector in the ith direction. So in other words, we can estimate del C del Wi by computing the cost for two slightly different values of Wi, and then applying the gradient calculation. So this same idea can be used to compute the partial derivative del C del B with respect to the biases as well. That is when the term is del C and del B, B represent the bias here. The same kind of calculation can be performed there as well. So this approach looks very promising and simple to understand, and would not take more than 3 or 4 lines of code. But then there's a problem here, and let's understand what is that. So imagine for a real-world case, we have a million weight, and so that means to calculate these terms, we have to calculate these W, the changed weight, W plus epsilon I, and W, and the entire gradient a million times. That means that to compute the gradient, gradient at the end, we need to compute the cost function a million different times, requiring a million forward passes through the network for each training example. And that's where these the chain rule of backpropagation comes to save us, because it has a specific order of operation that is highly efficient. What's clever about backpropagation is that it enables us to simultaneously compute all the partial derivative of that is del C, and del Wi using just one forward pass through the network, followed by one backward pass through the network. And so the total cost of backpropagation is roughly the same as making just two forward passes through the network. Compare that to 1,000,001 forward pass with our previous original brute force method. All right, that was enough of the logic why we needed a chain rule to handle these hugely large backpropagation operations. So now let's start with the actual calculation of the chain rule. So this is our network. Going back to the original picture, that we have one input layer, one hidden layer, one output layer, and there are total 9 weights here, 3 from the input layer to the hidden layer. Sorry, 6, 1, 2, 3, 1, 2, 3, 6, 6 weights from input layer to the hidden layer, and then 3 weights from the hidden layer to the output layer. It's a very simple structure. And the absolutely simplified for this explanation here, but practically there will be multiple hidden layers. So now the loss here at the output will be, for this example, we will consider mean squared error defined as, second, just 1 second. Okay. We'll define the mean squared loss like this. MSC. And this is represented by the letter C here for this example only, is equal to y minus y hat whole square. And the predicted value, that is this y hat, is equal to, you remember that we already discussed that y predicted value is a weighted sum of the weights and the values at various nodes. So that would be A11 into W31. That is A11 here and W31 here, plus then I have A12 and W32. A12 into W32. Further, I have from this layer to this layer, so okay, plus A13 into W33. And remember, again, we already talked about this, that how this subscript number for the weight is determined. The first number is a number where it is going, and the second number, it is where it is coming from. So that's how this is determined. Okay, and now the hidden layer, for the hidden layer, this value A1, A12, and A13, how this is determined is, for this example, we will consider the sigmoid activation function. So A1 will be determined with a definition of activation function, which is 1 by 1 plus e to the power minus h11. So this is a hidden layer activation value for a sigmoid activation function. And what is my h11? That is this value. That would be the weighted sum, again, h11 equal to x1 into w11, because my h1 is being fed by these two weights, w11 from here and w21 from here. Okay, x1 into w11 plus x2 into w21. And now we want to find out how much of an effect of a change in the weight has on the cost function. That is the rate of change of the cost with respect to rate of change of a single weight. So that we can represent with the chain rule of differential calculus. Let's do that. So what I want to have is del C by del W1 1, and that can be represented as a multiplication of four different differential, which are as follows. I hat into del and the final one is del H11 with respect to relatively simpler way to remember this is that each of these factor cancels out, like del y hat cancels out with del y hat here, and similarly here and here. So this is as a result of the chain rule that we discussed earlier. So essentially we are just performing a chain of differentiation to fetch the differentiation of our interest. So all these individual differentiation, that is four components, ultimately gives the differentiation that we want, which is del C by del W11. And then the question is why we are doing all these four different individual component wise differentiation, and the answer is that we create a chain so that each individual partial derivative can be easily calculated, and thereby we get the derivatives of two variables which are not directly connected, that is del C, and that is this cost function. Change of the cost function is not directly connected with the change of the weight W11, but with this application of chain rule we can actually connect it by individually calculating the four different components and get what we want. That is, we want the change of loss with respect to change of a single weight. And now the next task is to calculate each of these separate components differentiation. That is, we need to derive what exactly is del C del y hat, what exactly is del y hat del A11, and so on and so forth for each of these 1, 2, 3, 4 components. So let's start with the first one, which is del C with respect to del y hat. And that we already had the equation of del y. We already have the equation y hat. So now let's do this. The first one, that is number 1, is del C by y hat equal to we need to calculate the loss. The loss in this case, that is, we know the value of C. Let's do this. And by replacing the value of C, we get y minus y hat whole square. And this comes to minus 2 into y minus y hat. And how we get this? It's just a power rule of differentiation, that is ddx of nx to the power n is equal to nx to the power n minus 1. Okay, so that one is done, and now go to the next one, which is del y hat by del A11. Okay. So del y hat will mean del A 11. We already earlier saw the value of y hat, which we can see here again. Yes, so this is earlier we discussed that this y hat, that is output value from the final output layer, is a weighted sum of all these individual values and multiplied by the weight. So let's have the same value here as well. So is equal to del A11. I'm just replacing the exact value of y hat here. Instead of the y hat, I'm just putting that value plus I think that is slightly wrong here. That would be A11 multiplied by the first two, it was 3, 1 plus A12. The second weight is W32. And the third one is A13 multiplied by W33. So if you simplify this by applying the very first principle of differentiation, you will get this value, W31. Okay, so we are done with the number 2 from our this is what we are trying to simplify. So we are done with the number 1 and number 2. Now we have to go to the third one, which is del A11 del. And remember what was our H11? That was the value derived after applying the sigmoid function. So this was our value of A11 and H11. H11 is just the weighted sum of the weights and the value of x1 and x2. And A11 is the result of applying the sigmoid activation function. So we have to know the derivative of a sigmoid function, and that we can let's forget this line for now. First see what is the derivative of a sigmoid function, and that is if sigmoid function is del x equal to 1 by 1 plus minus x. If we take the dx of this, that is dx of sigma x will be the sigmoid function itself, then multiplied 1 minus. Okay, so this can be derived with a mathematical formulation, and there's a detailed mathematical derivation. I will give the link in the description, and this is that derivation which from math stack exchange, one of the question here. So you can see that the dx of the sigma x, after doing all this calculation, we arrive at this final form. So in our case, that means our del A11 with respect to del H11 would be A11 into 1 minus A11. Remember, the value of H is an input to the function A11. So that's how the sigmoid activation function is calculated. All right, so we are done with number 3 as well. Now we are left with the fourth and final component, which is del H11 and with respect to del W11. That was the last in the chain rule. That was the last component of the earlier expression we saw. So that we already know the value of H11 as we discussed just now. It's the weighted sum of X1 W1 and X2 W21. So let's do that. W11 replace the value of H11, which is X1 multiplied by W11 plus X2 multiplied by W21. And again, if we simplify this, we will be left with X1 here. Okay, so now we got all the four components of our earlier expression for the chain rule. So what we just did is this was our chain rule. Let me change the color. So this is our expansion for calculating the rate of change of cost with respect to a single weight W11, and we just calculated now the individual values of these four individual partial differential expressions. Now to calculate the final, to get the result of what it means, we just need to multiply all the individual results that we got. So let's do that. So finally, del C by del W11 means the first differentiation was 2 multiplied by y minus y hat. And the second differentiation was just W31. Third differentiation was A on 1. And the final was, sorry, the third differentiation itself was A11 because that was a sigmoid function. So A11 into 1 minus A11. So this entire expression was our third differentiation. That is the sigmoid function. And the last differentiation was just x1. Okay, so this is our final form of del C del W1. So what we can see from this final expression, simplified expression version of this, that we are now able to calculate the impact on the loss value of a small change in the weight value, that is a gradient of the loss with respect to a weight, without brute forcing our way by recomputing the feed-forward propagation for each and every weight. So now with a single step, we can calculate this gradient, that is a rate of change of loss with respect to a rate of change of a single weight. But in our brute forcing process earlier, what we discussed, we had to calculate, if we had million weights, we had to calculate the loss function for each of those million weights. So that would have been hugely much more inefficient. And now the final part of updating the weights for during the backpropagation process. Like we discussed, that the whole backpropagation process is about updating the weight so that the loss becomes lower and lower gradually. So after we get this gradient, so this whole part is our gradient. Now the final weight for we update the weight like this. So updated weight, updated W is original W minus learning rate LR into this value, that is del C by del WI. Okay, so this W would be I because we are going through the weights. Okay. All right, that's how the chain rule is implemented. And in this video, my purpose was to arrive at the chain rule, the mathematical derivation of that. In a separate video, we will go through actual Python implementation of the backpropagation process for a very simple neural network architecture. So in the next video, we will take the same neural network that we have here, that is one input layer and one hidden layer, one output layer, and do this whole process of backpropagation by application of the chain rule and Python implementation of the same. Thank you very much.